Biotrophic pathogens. These pathogens, such as rusts, powdery mildews, and viruses, feed on living plant tissue without killing the host cell immediately. Biotrophic pathogens can be effectively managed by systemic acquired resistance (SAR) and the production of antimicrobial compounds. Necrotrophic pathogens. Necrotrophic pathogens, such as Botrytis and Fusarium, kill plant cells to obtain nutrients. These pathogens can be controlled through jasmonic acid (JA) mediated responses, the hypersensitive response (HR), and the activation of defensive enzymes like chitinases and glucanases. Hemabiotropic pathogens. These pathogens, such as Ralstonia solanacearum, initially behave as biotrophs but later switch to a necrotrophic mode as they kill the plant tissue. They are controlled by both SAR and JA pathways. 3. Key molecular and cellular responses to pathogen attack. Reactive oxygen species ROS, including hydrogen peroxide (H2O2) and superoxide anion (O2-), are produced during the hypersensitive response (HR) and contribute to pathogen killing by disrupting the pathogen's cellular machinery. Pathogenesis-related PR proteins. These include chitinases, glucanases, and PR1 proteins, which act directly to degrade pathogen cell walls or inhibit pathogen growth. Cell wall strengthening. The synthesis of lignin, callose, and other cell wall components is enhanced to limit pathogen entry and growth. 4. Previous year CSIR net questions. 1. Which of the following plant hormones is primarily associated with defense against necrophobic pathogens? A. Salicylic acid. B. Jasmonic acid, C. Cytokinin dioxin. Answer. B. Jasmonic acid, CSIR net Life Sciences, December 2019. 2. The hypersensitive response in plants is associated with which of the following? A. Programmed cell death and rose production. B. Increased pathogen proliferation. C. Systemic acquired resistance. D. Necrotrophic pathway activation. Answer. A. Programmed cell death and rose production. CSIR net Life Sciences, June 2020. 3. Which of the following secondary metabolites acts as an antimicrobial compound produced in response to pathogen attack? A. Tannin. B. Phytolexin. C. Chlorophyll D. Proteinase inhibitor. Answer. B. Phytolexin. CSIR net Life Sciences, June 2018. Conclusion. The plant responses to biotic stress, particularly pathogen attacks, are highly complex and involve an integrated network of signaling pathways, including hormonal regulation (SA), YA, ET physical barriers, and biochemical defenses. Understanding these mechanisms is critical for developing strategies to improve plant resistance to pathogens and enhance crop productivity. You said. Insects. ChatGPT said. Stress physiology. Responses of plants to biotic stress. Herbivora by insects. Insects are one of the most common biotic stressors to plants, affecting their growth, development, and reproduction. Herbivora, or the consumption of plant tissue by insects, can lead to significant damage, both directly and indirectly. Direct damage occurs when insects physically consume plant tissues, while indirect damage results from the plant's stress responses, which can affect its overall fitness. Plants have evolved various mechanisms to defend against insect herbivores, ranging from physical barrier defenses and induced responses that activate when herbivores attack. 1. Mechanisms of plant defense against insects. Plants have developed two main types of defense mechanisms to protect themselves from herbivores. Preformed defenses, those that are present before the herbivore attack, and induced defenses, those activated in response to herbivore attack. Preformed defenses. Preformed defenses are intrinsic mechanisms that are already present in plants, which help reduce the likelihood of herbivore attack or damage. Physical defenses. Trichomes, hair-like structures. Many plants possess trichomes, which can physically deter herbivores by making the plant's surface harder to feed on. These structures can be glandular, secreting toxic or sticky substances, or non-glandular, acting as a mechanical barrier. Thorns and spines. These are sharp, pointed structures on the plant's surface that physically prevent herbivores from consuming plant tissue. Thickened cuticles and epidermal layers. A thicker cuticle or outer skin layer can make it more difficult for insects to penetrate the plant's surface. Chemical defenses. Tannins. These are phenolic compounds that have astringent properties, binding to proteins in insect digestive systems, thereby inhibiting digestion and reducing the nutritional value of the plant tissue. Alkaloids. Alkaloids, such as nicotine in tobacco and caffeine in coffee, act as toxins that can deter or kill herbivores. Terpenoids. These are volatile compounds, like limonene and menthol, which can have insecticidal properties or act as repellents. Protease inhibitors. These chemicals interfere with the digestive enzymes of herbivores, preventing them from digesting proteins efficiently. B-induced defenses. Induced defenses are activated when the plant detects the presence of herbivores. These defenses are typically more specific and robust than preformed defenses. Herbivore recognition and signaling. Plants have evolved pattern recognition receptors (PRRs) that can recognize herbivore-induced molecular patterns, such as the saliva proteins secreted by insects. Upon recognition, plants activate defense mechanisms through signaling molecules like jasmonic acid (JA). Jasmonic acid (JA). This hormone is central to the plant's response to herbivora. When plants are damaged by herbivores, YA is synthesized and triggers the expression of defense genes that help to protect the plant. JA plays a key role in activating defenses against both insects and pathogens. Systemic acquired resistance (SAR) and systemic defense signaling. Similar to how plants respond to pathogens, herbivore can induce systemic acquired resistance (SAR). This involves the activation of defense genes not only at the site of injury but also in distant part of the plant, preparing the plant for future attacks. Green leaf follicles (GLBs). When plants are damaged, they release specific follicles that serve as warning signals to neighboring plants and attract natural enemies like parasitoid wasps that prey on herbivores. Production of defense proteins. Proteinase inhibitors. These inhibit the enzymes required by herbivores to digest proteins, thus limiting the nutritional value of the plant tissue. Chitinases. These enzymes degrade chitin, a major component of insect exoskeletons, thereby reducing the herbivore's ability to maintain its external structure and survive. Lipid transfer proteins. These are involved in the defense against insects by disrupting the feeding mechanisms of herbivores. Induced structural changes. Callose deposition. Plants can deposit callose at the site of insect feeding, forming a physical barrier that limits the movement of herbivores. Cell death hypersensitive response. In some cases, plants undergo programmed cell death in response to herbivore attack, restricting the spread of damage. 2. Induced secondary metabolites and defense pathways. Plants often produce secondary metabolites in response to herbivora. These compounds serve as defense mechanisms to deter herbivores or to directly inhibit their growth and reproduction. Phenolics. Compounds such as flavonoids, tannins, and lignans have antimicrobial properties and act as toxins or deterrents to herbivores. They may also interfere with the digestion of plant material by herbivores. Alkaloids. These are potent chemical defenses that are toxic to herbivores. Caffeine, nicotine, and morphine are examples of alkaloids that serve as plant defenses against herbivora. Terpenoids. These compounds, including essential oils, have insecticidal properties or act as feeding deterrents. Some monoterpenes and sesquiterpenes are known to repel herbivores and attract predators of the herbivores. 3. Plant-herbivore interactions and coevolution. The interaction between plants and herbivores often leads to a coevolutionary arms race, where both the plant and the herbivore evolve new strategies to outcompete each other. For example, herbivore adaptations. Some insects have evolved mechanisms to detoxify or tolerate plant defenses, such as the ability to metabolize toxins or feed on toxic plants without being harmed. Certain herbivores, like caterpillars, are capable of sequestering toxic compounds, e.g., alkaloids from plants and using them as a defense against their own predators. Plant adaptations. In response to herbivores, plants may evolve new forms of chemical resistance or deterrence. For example, some plants increase their production of secondary metabolites or develop structural defenses like spines or tougher leaves. 4. Previous year CSIR net questions. 1. Which of the following is the primary function of jasmonic acid (YA) in plants during herbivore attack? A. Inhibition of photosynthesis. B. Activation of systemic acquired resistance. C. Activation of defense responses. D. Promotion of cell division. Answer. C. Activation of defense responses. CSIR net Life Sciences, December 2019. 2. Which of the following secondary metabolites is primarily involved in defense against herbivores? A. Flavonoids. B. Tannins. C. Terpenoids. D. All of the above. Answer. D. All of the above. CSIR net Life Sciences, June 2020. 3. The hypersensitive response (HR) in plants is a defense mechanism primarily associated with which of the following? A. Pathogen defense. B. Insect defense. C. Abiotic stress. D. Both A and B. Answer. D. Both A and B. CSIR net Life Sciences, June 2018. Conclusion. Plants have evolved a complex and multifaceted defense system to cope with insect herbivora. These defenses include physical barriers, chemical deterrents, and induced responses mediated by hormonal pathways such as jasmonic acid. By understanding these defense mechanisms, we can improve agricultural practices to protect crops from insect pests and ensure sustainable crop production. You said. Abiotic water. ChatGPT said. Stress physiology. Responses of plants to abiotic stress. Water stress. Water is an essential component for plant growth, and its availability directly affects various physiological processes in plants. However, under conditions of water stress, both drought and flooding, plants undergo a variety of physiological and biochemical changes to adapt to these adverse conditions. Water stress can significantly impact plant metabolism, growth, and development, leading to reduced productivity. The plant responses to water stress are classified into avoiding, tolerating, and recovering mechanisms, which involve a wide range of physiological and molecular adaptations. 1. Water stress, types and impact on plants of drought stress. Drought stress occurs when the water supply to plants is limited, leading to water deficiency in plant tissues. This can result from reduced rainfall, high temperatures, or poor soil conditions. Drought stress triggers several responses in plants, including dehydration. As the water content of plant cells decreases, the cellular functions start to be disrupted. The plant's ability to photosynthesize, take up nutrients, and grow is compromised. Osmotic stress. Reduced water availability leads to a reduction in turgor pressure, affecting cell expansion and growth. Cellular damage. Drought conditions lead to oxidative stress due to the overproduction of reactive oxygen species, ROS, causing damage to cellular components such as membranes, proteins, and DNA. B. Flooding stress. Flooding stress occurs when the soil is saturated with excess water, reducing the availability of oxygen to plant roots. This leads to oxygen deficiency. The lack of oxygen in waterlogged soils hampers root restoration and affects the plant's ability to take up nutrients and water. Root rot. Prolonged flooding can result in root decay due to the limited oxygen supply, leading to reduced nutrient uptake and potential death of the plant. Stomatal closure. Plants often close their stomata under waterlogging conditions to prevent further water loss, but this also reduces CO2 intake, affecting photosynthesis. 2. Mechanisms of water stress tolerance in plants. Plants employ various physiological, biochemical, and molecular mechanisms to cope with water stress. These mechanisms can be broadly categorized as avoidance, tolerance, and recovery strategies. A water stress avoidance mechanisms. Water stress avoidance involves strategies that reduce water loss or limit the extent of dehydration. Leaf modifications. Leaf curling or wilting. Plants may curl their leaves or exhibit wilting to reduce the surface area exposed to the atmosphere, thereby reducing transpiration. Stomatal closure. Plants close their stomata to prevent water loss through transpiration. This mechanism is typically mediated by the hormone abscisic acid ABA. Leaf rolling. Some plants, especially grasses, roll their leaves to reduce the surface area exposed to the sun and reduce transpiration. Root modifications. Root deepening. Some plants develop deeper roots to access water from deeper soil layers. This is especially useful in dry environments where surface water is scarce. Increased root growth. The root system may become more extensive to increase the surface area for water absorption, allowing the plant to access any available water. B. Water stress tolerance mechanisms. Water stress tolerance mechanisms help plants survive under drought or flooding conditions by minimizing the damage caused by reduced water availability. Osmotic adjustment. Plants accumulate osmolytes, e.g., proline, glycine, betaine, sugars in their cells, which helps to retain water and maintain turgor pressure. These compounds act as osmoprotectants, stabilizing proteins and cellular structures. Solute accumulation. During drought stress, plants accumulate solutes such as potassium, sodium, and sugars to maintain osmotic balance and protect cellular integrity. Antioxidant defense systems. Reactive oxygen species, ROS, are generated during water stress, leading to oxidative damage. Plants have developed antioxidant systems, including superoxide dismutase, SOD catalase CAT, and ascorbic peroxidase APX to scavenge these harmful molecules and protect cellular components. Obviated stress responses. Abscisic acid ABA is a key hormone that regulates plant responses to water stress. ABA levels increase under drought conditions, leading to the closure of stomata, reduction in transpiration, and activation of stress-related genes that enhance tolerance to dehydration. Gene expression changes. Water stress triggers the expression of specific stress-related genes, including heat shock proteins, HSPs, late embryogenesis abundant proteins, lead proteins, and dehydrins, which help in protein stabilization and protection against dehydration-induced damage. Membrane stability. During water stress, plants enhance the stability of cell membranes by modifying membrane lipids, making them more resistant to damage caused by dehydration. This helps maintain cellular function under low water conditions. C. Recovery from water stress. Recovery involves restoring normal physiological functions after the stress has subsided. Once the plant receives water, conditions improve. The following processes occur. Stomatal reopening. Upon rehydration, plants reopen their stomata to resume transpiration and CO2 uptake for photosynthesis. Reestablishment of photosynthesis. Recovery from water stress involves the reactivation of photosynthetic machinery and resumption of normal metabolic activity. Resynthesis of cellular components. Following rehydration, plants restore the synthesis of proteins, enzymes, and other cellular components that may have been damaged during stress. 3. Key hormones involved in water stress responses. Abscisic acid ABA. ABA is a central plant hormone involved in water stress. It regulates stomatal closure, triggers the expression of stress-related genes, and helps in osmotic adjustment by promoting the accumulation of compatible solutes. Cytokinins. These hormones are involved in cell division and growth but can also have a role in drought responses by modulating the balance of water between the root and shoot systems. Auxins. Auxins can regulate root development, which plays a role in enhancing water uptake under stress conditions. Ethylene. Ethylene is involved in regulating plant responses to various stressors, including waterlogging. It can promote root growth and help the plant adapt to low oxygen conditions. 4. Previous year CSIR net questions. 1. In response to water stress, the accumulation of which of the following compounds helps plants to maintain osmotic balance? A. Sucrose. B. Proline. C. Fructose. D. Glucose. Answer. B. Proline. CSIR net Life Sciences, June 2020. 2. Which of the following is a major role of abscisic acid ABA during drought stress? A. Promotion of photosynthesis. B. Stomatal closure. C. Increased root growth. D. Suppression of osmotic adjustment. Answer. B. Stomatal closure. CSIR net Life Sciences, December 2019. 3. Which of the following is not a typical response of plants to flooding stress? A. Reduced transpiration. B. Root rot. C. Oxygen deficiency. D. Increased photosynthesis. Answer. D. Increased photosynthesis. CSIR net Life Sciences, June 2018. Conclude. Water stress, whether due to drought or flooding, has a profound impact on plant physiology. Through a combination of avoidance, tolerance, and recovery mechanisms, plants can survive and even thrive under these conditions. These mechanisms are driven by a complex network of hormones, osmotic adjustments, oxidant systems, and genetic changes that allow plants to mitigate the effects of water stress and recover once favorable conditions are restored. Understanding these processes is crucial for improving crop resilience to changing environmental conditions, especially in the face of climate change. You said, temperature. ChatGPT said. Stress physiology, responses of plants to abiotic stress, temperature stress. Temperature is a key environmental factor that affects plant growth, development, and productivity. Plants have evolved to survive within a specific range of temperatures, with extreme temperatures either heat or cold leading to various stress responses. Temperature stress is categorized into heat stress, excessive heat, and cold stress, low temperatures, and each type induces different physiological and biochemical changes in plants. Understanding how plants respond to temperature extremes is crucial for improving crop productivity, particularly under the increasing pressures of climate change. 1. Temperature stress, types and impact on plants of heat stress. Heat stress occurs when temperatures exceed the plant's optimal range, usually above 35 degrees Celsius. Heat stress leads to a variety of changes in plant physiology and biochemistry. Protein denaturation. High temperatures cause proteins to unfold and lose their functional conformation. This can lead to the inactivation of enzymes and disruption of cellular structures. Membrane instability. High temperatures increase the fluidity of cell membranes, making them more susceptible to damage. This can lead to the leakage of ions and solutes, disrupting cellular integrity. Oxidative stress. Heat stress leads to the overproduction of reactive oxygen species, ROS, which can cause damage to cellular components such as lipids, proteins, and nucleic acids. Reduced photosynthesis. Heat stress often leads to stomatal closure, limiting CO2 uptake and decreasing photosynthetic efficiency. Additionally, heat denatures photosynthetic proteins, further reducing photosynthetic capacity. B. Cold stress. Cold stress, which includes both chilling stress, exposure to temperatures above freezing but below the optimal range, and freezing stress temperatures below freezing, affects plant growth and survival in different ways. Membrane damage. Low temperatures can cause lipid bilayers to gel, leading to membrane rigidity and loss of membrane function. Protein denaturation. Just like heat stress, cold stress can cause proteins to denature, though the mechanisms differ. In freezing conditions, ice crystals can form inside plant cells, causing mechanical damage. Reduced enzyme activity. Low temperatures can reduce the activity of enzymes involved in various metabolic processes, slowing down the rate of physiological activities like photosynthesis and respiration. Desiccation. In freezing conditions, ice formation can lead to dehydration of cells, as water in the extracellular spaces freezes, making it unavailable for cellular processes. 2. Mechanisms of temperature stress tolerance in plants. Plants employ various physiological, biochemical, and molecular strategies to survive under temperature stress conditions. These mechanisms can be divided into avoidance, tolerance, and recovery mechanisms. A heat stress tolerance mechanism: heat shock proteins (HSPs). Heat stress induces the expression of heat shock proteins (HSPs), which act as molecular chaperones. These proteins help in the refolding of denatured proteins, prevent protein aggregation, and protect cellular structures from heat-induced damage. HSP70 is one of the key HSPs involved in heat stress tolerance. Membrane stabilization. Heat stress causes increased membrane fluidity. To counteract this, plants can modify their membrane lipid composition by increasing the proportion of unsaturated fatty acids, which helps in maintaining membrane stability under heat stress conditions. Osmotic adjustment. Similar to water stress, heat stress often triggers the accumulation of osmolytes such as proline, trehalose, and glycine betaine, which help in maintaining cell turgor and stabilizing cellular proteins and membranes under high temperatures. Antioxidant defense system. Reactive oxidant species ROS are produced during heat stress, leading to oxidative damage. Plants have evolved antioxidant defense mechanisms, including superoxide dismutase, SOD catalase CAT, and ascortate peroxidase APX, which scavenge ROS and minimize oxidative damage. Stomatal regulation. In response to heat stress, plants may close their stoma to reduce water loss through transpiration, which helps in maintaining water balance, but also reduces CO2 intake and affects photosynthesis. This regulation is often mediated by abscisic acid ABA. B cold stress tolerance mechanisms: cold acclimation. Plants can undergo a process called cold acclimation, in which they gradually adjust to colder temperatures by altering their biochemical pathways. This involves the synthesis of protective proteins such as dehydrins, which help stabilize cellular structure, protect against freezing damage. Membrane lipid composition. Cold adapted plants modify their membrane lipids by increasing the proportion of unsaturated fatty acids, which prevents membrane rigidity at low temperatures. This ensures membrane fluidity and proper cellular function even at low temperatures. Antifreeze proteins (AFPs). Some plants produce antifreeze proteins (AFPs) that bind to ice crystals and prevent their growth, thus preventing ice formation inside plant cells. AFPs are particularly important in plants exposed to freezing stress. Production of osmolytes. Similar to heat stress, cold stress also induces the accumulation of osmoprotectants like proline, trehalose, and sucrose. These molecules help to maintain cell hydration and protect cellular proteins from cold-induced damage. Stabilization of enzyme activity. Cold stress can reduce enzyme activity, so plants produce specific proteins that help stabilize enzymes and maintain their activity at low temperatures. Desiccation tolerance. In freezing conditions, ice can cause desiccation, loss of water in plant cells. Plants can produce compatible solutes that help to maintain cellular hydration and prevent damage from dehydration. 3. Key hormones involved in temperature stress responses: abscisic acid ABA. ABA plays a central role in both heat and cold stress responses. It regulates stomatal closure to prevent water loss during heat stress and enhances the synthesis of protective proteins during cold stress. ABA also modulates the expression of genes involved in osmotic adjustment. Auxins. Auxins are involved in regulating growth, and their levels decrease during heat stress. They help in modulating root growth to enhance water uptake during drought or heat stress. Gibberellins. The levels of gibberellins often decrease under heat and cold stress, as these hormones are involved in promoting growth. Low levels help conserve energy and resources during stress conditions. Cytokinins. Cytokinins are involved in cell division and differentiation. Under heat stress, cytokinins can help in maintaining cell viability and function by delaying senescence and promoting growth in non-stressed tissues. 4. Previous year CSIR net questions. 1. Which of the following is a heat stress-induced protein that helps in protein folding? A. Dehydrin. B. Heat shock protein HSP. C. Antifreeze protein D. Osmotic regulator. Answer. B. Heat shock protein HSP. CSIR Net Life Sciences, December 2019. 2. Cold acclimation in plants primarily leads to the production of which of the following? A. Heat shock proteins. B. Antifreeze protein. C. Osmolytes. D. Chlorophyll. Answer. B. Antifreeze proteins. CSIR Net Life Sciences, June 2020. 3. Which of the following compounds plays a significant role in maintaining membrane stability under high temperature stress? A. Saturated fatty acids. B. Unsaturated fatty acids. C. Starch. D. Sugars. Answer. B. Unsaturated fatty acids. CSIR Net Life Sciences, December 2018. Conclusion. Temperature stress, whether from excessive heat or extreme cold, significantly affects plant survival and productivity. Through a combination of avoidance, tolerance, and recovery mechanisms, plants have evolved strategies to mitigate the damaging effects of temperature extremes. Understanding these responses, particularly the roles of heat shock proteins, antifreeze proteins, osmolytes, and hormonal regulation, is essential for developing crops that are resilient to the challenges posed by a changing climate. You said, salt stresses. ChatGPT said. Stress physiology, responses of plants to abiotic stress, salt stress. Salt stress is a major abiotic stress affecting plant growth, productivity, and development. It occurs when the concentration of salts, particularly sodium chloride, NaCl, in the soil exceeds levels that are tolerable for plants. Salt stress can occur in regions with poor irrigation practices, high evaporation rates, or saline soils. This stress can negatively impact plants at various levels, from cellular to systemic, leading to reduced crop yields in saline environments. The ability of plants to cope with salt stress is crucial for agriculture in regions affected by salinity. 1. Types of salt stress. Salt stress in plants is classified into two main categories based on the concentration of salt. Osmotic stress. In this early stage, salt accumulation in the soil solution reduces the availability of water for plant roots, creating a water deficit within the plant. As a result, plants face difficulty in absorbing water, leading to dehydration and reduced turgor pressure. B. Ionic stress. When salts such as sodium, Na+, and chloride Cl ions accumulate in plant tissues, they disrupt cellular homeostasis. These ions can cause toxicity and interfere with essential cellular processes, including enzyme function, protein synthesis, and ion balance, leading to ionic imbalance and toxicity. 2. Mechanisms of salt stress response in plants. Plants exhibit several mechanisms to cope with salt stress. These mechanisms include salt exclusion, osmotic adjustment, ion compartmentalization, and protective protein synthesis. The main challenge for plants under salt stress is to maintain ion homeostasis while dealing with both osmotic and ionic stress. A salt exclusion. Some plants, especially halophytes, can exclude salts from entering their tissues by limiting the uptake of sodium, Na+, and chloride Cl ions through their roots. This is achieved through specialized ion transport mechanisms of the root cell membranes, such as ion channels and transporters. Roots of salt-sensitive plants can express specific ion channels or transporters that prevent the uptake of Na+ and Cl. For example, the Na+, H+ antiporter in the root plasma membrane helps in expelling Na+ ions from the cytoplasm. Root membrane integrity. Salt-tolerant plants can maintain root membrane integrity, preventing excessive ion influx. They often have an adaptive ability to form thick root cell walls, which can limit salt uptake. B. Osmotic adjustment. Salt accumulation in plant tissues reduces water potential, leading to dehydration. Plants respond to this by accumulating osmolytes, low molecular weight compounds that help maintain cell turgor and prevent dehydration. Common osmolytes involved in osmotic adjustment during salt stress include proline. Proline accumulation is one of the most important responses to salt stress. It acts as an osmolyte, stabilizing proteins and membranes and protecting plant cells from oxidative damage. Sugar alcohols, e.g., sorbitol, trehalose. These compounds also serve as osmotic regulators, stabilizing cellular structures under salt stress conditions. C. Ion compartmentalization. Plants often compartmentalize harmful ions like sodium, Na+, and chloride Cl in vacuoles, isolating them from the cytoplasm and preventing cellular damage. This is mediated by specialized transporters. Na+, H+ antiporter SOS1. This transporter helps in sequestering excess sodium into vacuoles or expelling it outside the plant cell. It is a crucial component of salt tolerance mechanisms in plants. Vacuolar Na+, H+ antiporter. The vacuolar Na+, H+ antiporter VAPs pumps Na+ ions into vacuoles, maintaining cytoplasmic Na+ levels at a low concentration and preventing ionic toxicity. Desalt-induced protective protein synthesis. Under salt stress, plants produce protective proteins that help to mitigate cellular damage. These include heat shock proteins HSPs. In addition to heat stress, HSPs also protect plants from salt-induced oxidative damage by stabilizing proteins and assisting in protein folding. Late embryogenesis of abundant proteins. These proteins help to protect the plant from dehydration and stabilize cellular structures. Antioxidants. Salt stress often leads to the generation of reactive oxygen species ROS. Plants have antioxidant defense systems, including enzymes like superoxide dismutase, SOD catalase CAT, and ascortate peroxidase APX, which scavenge ROS and reduce oxidative stress. 3. Hormonal regulation in salt stress responses. Various plant hormones play a significant role in mediating the response to salt stress. These hormones regulate various physiological processes such as ion homeostasis, osmotic adjustment, and stress tolerance. Abscisic acid ABA. ABA is the key hormone in the regulation ABA is the key hormone in the regulation of plant responses to environmental stresses, including salt stress. ABA controls stomatal closure. Under salt stress, ABA induces stomatal closure to minimize water loss through transpiration. Expression. ABA regulates the expression of stress-responsive genes, including those involved in osmotic adjustment and ion transport. B. Auxins. Auxins are involved in modulating root architecture, and their role in salt stress involves regulating root elongation. Salt stress generally reduces auxin levels, which can lead to reduced root growth, thereby limiting the uptake of salt. C. Cytokinins. Cytokinins are involved in promoting cell division and shoot growth. During salt stress, cytokinins may reduce plant growth to conserve resources. They also modulate the synthesis of stress-related proteins. D. Ethylene. Ethylene plays a dual role in salt stress responses. While it can induce senescence and program cell death important for detoxification, it can also stimulate root growth and other stress responses in certain plants. 4. Previous year CSIR net questions. 1. Which of the following is an important strategy used by halophytes to tolerate salt stress? Excessive transpiration. B. Salt exclusion. C. Increased photosynthesis. D. Inhibition of root growth. Answer. B. Salt exclusion. CSIR net Life Sciences, June 2020. 2. During salt stress, the accumulation of which of the following osmolytes helps in osmotic adjustment? A. Chlorophyll. B. Proline. C. Glucose. D. Starch. Answer. B. Proline. CSIR net Life Sciences, December 2019. 3. Which of the following ion transporters helps in compartmentalizing sodium ions in vacuoles to avoid toxicity during salt stress? A NA plus K plus pump. B. NA plus H plus antiporter CH plus FACE DCA2 plus H plus antiporter. Answer. B. NA plus H plus antiporter. CSIR net Life Sciences, December 2018. 5. Conclusion. Salt stress is a significant abiotic stress that hampers plant growth by causing osmotic and ionic imbalances. Plants employ a variety of mechanisms, including salt exclusion, osmotic adjustment, ion compartmentalization, and the synthesis of protective proteins to mitigate the effects of salt stress. Understanding these mechanisms and the role of hormonal regulation in salt stress tolerance is crucial for developing salt-tolerant crops. The accumulation of osmolytes like proline, the role of antioxidants in oxidative stress, and the activity of ion transporters like NA plus H plus antiporters are key factors in plant adaptation to saline environments. You said. System physiology, animal blood and circulation. ChatGPT said. System physiology, animal blood and circulation. The circulatory system in animals is a complex network responsible for the transportation of nutrients, gases, hormones, and waste products throughout the body. This system plays a critical role in maintaining homeostasis and supporting cellular functions. Blood, the medium of circulation, consists of plasma, cells, and platelets, each playing distinct roles in the circulatory process. 1. Components of blood. Blood is composed of the following key components. A. Plasma. Plasma is a liquid part of blood, accounting for approximately 55% of its volume. It is a yellowish fluid that consists of water. 90% water is the primary solvent, and it helps maintain blood volume and pressure. Proteins 7-8%. Plasma proteins include albumin, maintains osmotic pressure and transports molecules. Globulins, function in immune responses. Antibodies. Fibrinogen, involved in blood clotting. Electrolytes, sodium, Na plus potassium, K plus calcium, Ca2 plus bicarbonate, HCO3, maintain osmotic balance and pH. Nutrients, glucose, amino acids, vitamins, and fatty acids. Waste products, urea, carbon dioxide, CO2, and creatinine. Gases, oxygen, O2, and carbon dioxide, CO2, though in smaller quantities. B. Blood cells. Red blood cells, RBCs, also known as erythrocytes. RBCs are responsible for transporting oxygen from the lungs to tissues and returning carbon dioxide from tissues to the lungs. They contain hemoglobin, a protein that binds to oxygen. White blood cells, WBCs, also called leukocytes. WBCs are part of the immune system and protect the body against infections and foreign invaders. They include neutrophils, phagocytized bacteria and debris. Lymphocytes, involved in adaptive immunity, B cells and T cells. Monocytes, differentiate into macrophages that engulf pathogens. Eosinophils, involved in allergic responses and parasitic infections. Basophils, release histamine during allergic reactions. Platelets, thrombocytes, platelets are involved in blood clotting. They aggregate at the site of vascular injury, release clotting factors, and form a fibrin clot to prevent excessive blood loss. 2. Circulatory system and types of circulation. The circulatory system can be classified into two broad types. A. Open circulatory system. In an open circulatory system, blood or hemolymph is not confined to vessels. It circulates freely within body cavities, coming into direct contact with tissues and organs. This system is common in arthropods, e.g., insects, spiders, and some mollusks, e.g., clams. The heart pumps hemolymph into an open body cavity, where it bathes organs and returns to the heart. The lack of a well-defined vessel system limits the efficiency of nutrient and oxygen transport. B. Closed circulatory system. In a closed circulatory system, blood is confined to blood vessels. The heart acts as a pump to drive blood through a network of arteries, veins, and capillaries. This system is more efficient and is found in vertebrates, annelids, and cephalopods. The closed system allows for higher pressure and more effective transport of oxygen, nutrients, and waste products. Blood circulation occurs in a systemic circuit delivering oxygen to body tissues, and a pulmonary circuit delivering blood to the lungs for gas exchange. 3. Heart and blood vessels. The heart is the central pump of the circulatory system, composed of cardiac muscle that contracts rhythmically to circulate blood. The heart has 4 chambers in most vertebrates, 2 atria and 2 ventricles. A heart structure. Atria, the upper chambers that receive blood from the body and lungs. Ventricles, the lower chambers that pump blood out of the heart. Valves, valves prevent the backflow of blood. These include the tricuspid valve between right atrium and ventricle, pulmonary valve between right ventricle and pulmonary artery, mitral valve between left atrium and ventricle, and aortic valve between left ventricle and aorta. B. Blood vessels. Arteries carry oxygenated blood away from the heart to body tissues. Arteries have thick muscular walls to withstand high pressure from the pumping action of the heart. Veins carry deoxygenated blood back to the heart. Veins have thinner walls than arteries and contain valves ensure one-way blood flow. Capillaries, the smallest blood vessels where nutrient and gas exchange occurs between blood and tissues. The thin walls of capillaries allow for easy diffusion of gases and nutrients. 4. Mechanisms of blood circulation. The circulation of blood is controlled by various mechanisms. A cardiac cycle. The cardiac cycle consists of 2 main phases. Systole, the contraction phase when the heart pumps blood out. Diastole, the relaxation phase when the heart chambers refill with blood. B. Blood pressure. Blood pressure is the force exerted by blood against the walls of blood vessels, primarily arteries. It is determined by the cardiac output, volume of blood pumped by the heart per minute, and the resistance offered by the blood vessels. Blood pressure is measured in millimeters of mercury, mmHg, and typically represented as systolic, diastolic pressure, e.g., 120/80ths of a millimeter of mercury. Systolic pressure, the pressure when the heart contracts. Diastolic pressure, the pressure when the heart is at rest. C. Blood flow regulation. The regulation of blood flow is essential for maintaining homeostasis. This is achieved through mechanisms such as vasoconstriction, the narrowing of blood vessels to increase blood pressure and reduce flow to certain areas. Vasodilation, the widening of blood vessels to decrease blood pressure and increase flow to tissues. D. Lymphatic system. The lymphatic system works in tandem with the circulatory system to return excess interstitial fluid to the bloodstream. It also plays a key role in immune responses. The lymphatic system includes lymph nodes, lymph vessels, and lymph, which transports white blood cells, particularly lymphocytes, to fight infections. 5. Previous year CSIR net questions. 1. Which of the following blood components is responsible for the transport of oxygen? A. Platelets. B. White blood cells. C. Red blood cells. D. Plasma. Answer. C. Red blood cells. CSIR net Life Sciences, June 2021. 2. Which type of circulation involves blood being pumped into open spaces in the body? A closed circulatory system. B. Open circulatory system. C. Double circulatory system. D. Single circulatory system. Answer. B. Open circulatory system. CSIR net Life Sciences, December 2019. 3. Which of the following is the main function of capillaries? A. Carry blood away from the heart. B. Facilitate nutrient and gas exchange. C. Maintain blood pressure. D. Regulate body temperature. Answer. B. Facilitate nutrient and gas exchange. CSIR net Life Sciences, June 2018. 6. Conclusion. The circulatory system in animals is crucial for maintaining physiological balance by transporting essential substances such as oxygen, nutrients, and waste products. Blood, composed of plasma, cells, and platelets, facilitates these processes. The heart and blood vessels ensure that blood circulates efficiently throughout the body. Mechanisms like the cardiac cycle, blood pressure regulation, and the lymphatic system contribute to maintaining homeostasis. Understanding these processes is essential for comprehending animal physiology and its relevance to health and disease. You said. Blood corpuscles. ChatGPT said. Blood corpuscles, types and functions. Blood corpuscles, or blood cells, are the cellular components of blood responsible for various functions such as transporting gases, fighting infections, and aiding in clotting. Blood corpuscles can be categorized into three main types: red blood cells, RBCs, white blood cells, WBCs, and platelets. Each type has distinct roles in maintaining the body's health and physiological balance. 1. Red blood cells, RBCs, erythrocyte structure. Shape: RBCs are biconcave discs, which provide a large surface area for gas exchange. Size: the average diameter is about 7 to 8 micrometers. Lifespan: typically 120 days. Function: the primary function of RBCs is the transport of oxygen from the lungs to tissues and return of carbon dioxide from the tissues to the lungs for exhalation. RBCs contain hemoglobin, a protein that binds to oxygen molecules in the lungs and releases them in tissues with lower oxygen concentration. Hemoglobin also helps in the transport of carbon dioxide, where it binds CO2 and carries it back to the lungs, where it is expelled. Erythropoiesis. RBCs are produced in the red bone marrow through a process called erythropoiesis. The production is regulated by the hormone erythropoietin, which is released by the kidneys in response to low oxygen levels in the blood. Disposal. Older damaged RBCs are broken down in the spleen and liver, where hemoglobin is metabolized and the iron is recycled. 2. White blood cells, WBCs, leukocyte structure. WBCs are larger than RBCs and have a nucleus, unlike RBCs which are enucleate. They are usually colorless because they lack hemoglobin. WBCs are present in much smaller quantities compared to RBCs but are crucial for immune functions. Types of WBCs and their functions: neutrophils. Make up 55-70% of the total WBC count. These cells are the first line of defense during an infection and are phagocytic, engulf and digest pathogens, such as bacteria. Lymphocytes. Comprise 20-40% of the WBC population. These cells produce antibodies that recognize specific antigens, while T cells are involved in directly attacking infected cells or regulating the immune response. They are crucial for adaptive immunity. Monocytes. Represent 2-8% of the WBCs. They differentiate into macrophages in tissues, which are also phagocytic and play a role in immune response and inflammation. Eosinophils. Account for 1-4% of WBCs. They are involved in allergic reactions and parasitic infections. Basophils. Represent less than 1% of WBCs. These cells release histamine during allergic responses and contribute to inflammation. Function. The primary function of WBCs is defense against infections. They are involved in the body's immune response, identifying and neutralizing pathogens like bacteria, viruses, and fungi. Formation: leukopoiesis. WBCs are produced in the bone marrow, with some types also originating in the lymph nodes and spleen. Their production is influenced by various cytokines and growth factors such as colony-stimulating factors. 3. Platelets, thrombocyte structure. Platelets are cell fragments derived from larger cells called megakaryocytes in the bone marrow. They are small, irregularly shaped, and lack a nucleus. Function. Platelets are primarily involved in blood hemostasis. They form a plug at the site of a blood vessel injury and release clotting factors to aid in the formation of a fibrin clot, which prevents excessive blood loss. Mechanism of clotting. When a blood vessel is damaged, plate adhere to the exposed collagen fibers at the injury site. They release ADP, adenosine diphosphate, thromboxane E2, and other factors that activate nearby platelets. Platelets aggregate to form a platelet plug. The clotting cascade is activated, involving proteins like fibrinogen, which are converted into fibrin threads that stabilize the clot. Formation: thrombopoiesis. Platelets are produced in the bone marrow from megakaryocytes under the influence of the hormone thrombopoietin, primarily produced by the liver. 4. Blood cell counts and their significance. Red blood cells. Normal counts range from 4.7 to 6.1 million cells per microliter of blood in men and 4.2 to 5.4 million in women. White blood cells. Normal count ranges from 4,000 to 11,000 cells per microliter of blood. Platelets. Normal count ranges from 150,000 to 450,000 platelets per microliter of blood. Abnormal counts of any blood cell type can indicate various health conditions. Anemia, low RBC count, results in fatigue and weakness. Leukocytosis, high WBC count, may indicate infection or inflammation. Thrombocytopenia, low platelet count, increases the risk of bleeding. 5. Previous year CSIR net questions. 1. Which of the following blood components is primarily responsible for the immune defense of the body? A. Platelets. B. White blood cells, C. Red blood cells, D. Plasma proteins. Answer: B. White blood cells. CSIR Net Life Sciences, June 2020. 2. What is the primary function of platelets in the blood? A. Oxygen transport. B. Immune response. C. Blood clotting. D. Nutrient transport. Answer: C. Blood clotting. CSIR Net Life Sciences, December 2018. 3. The primary function of red blood cells is 2. A. Transport carbon dioxide. B. Transport oxygen. C. Fight infections. D. Form blood clots. Answer: B. Transport oxygen. CSIR Net Life Sciences, June 2019. 6. Conclusion. Blood corpuscles, including red blood cells, white blood cells, and platelets, perform critical functions for survival. RBCs are responsible for transporting oxygen, WBCs protect against infections, and platelets ensure proper blood clotting. A thorough understanding of these cells and their functions is crucial for studying animal physiology and the body's defense mechanisms. Any abnormalities in blood corpuscles can lead to serious medical conditions, underlying their importance in maintaining health and homeostasis. You said, hemopoiesis. ChatGPT said, hematopoiesis. Hematopoiesis, the formation of blood cells. Hematopoiesis, also known as hematopoiesis, is a process through which all the blood cells, including red blood cells, RBCs, white blood cells, WBCs, and platelets, are produced. This process primarily occurs in the bone marrow but can also take place in other organs like the liver and spleen under certain conditions, especially during fetal development or in pathological states. Hematopoiesis is regulated by a complex network of growth factors, hormones, and cytokines that ensure the proper formation, maturation, and differentiation of blood cells. 1. Site of hematopoiesis. Fetal development. In early fetal life, up to about 2 to 3 months, hematopoiesis takes place in the yolk sac. As development progresses, it shifts to the liver and spleen, and later, after birth, the bone marrow becomes the primary site. Adult life. In adults, hematopoiesis primarily occurs in the red bone marrow, located in the flat bones, such as the sternum, ribs, pelvis, and the ends of long bones like the femur. 2. Hematopoietic stem cells, HSCs. Pluripotent stem cells. The starting point for all blood cells is a hematopoietic stem cell, HSC, a multipotent stem cell found in the bone marrow. These HSCs are capable of differentiating into all types of blood cells. HSCs are self-renewing, meaning they can produce more HSCs, ensuring a continuous supply of new blood cells throughout life. Differentiation. HSCs give rise to 2 primary progenitor cell lines, myeloid progenitors and lymphoid progenitors. These progenitors further differentiate into various blood cell types under the influence of specific growth factors and cytokines. 3. Stages of hematopoiesis. Hematopoiesis occurs through a series of stages, with progenitor cells progressively differentiating into mature blood cells. A myeloid lineage. Myelopoiesis. Myeloid progenitor cells give rise to erythrocytes, RBCs, red blood cells that transport oxygen and carbon dioxide. Granulocytes, white blood cells involved in immune defense. These include neutrophils, the most abundant WBCs involved in phagocytosis of bacteria. Eosinophils, involved in allergic reactions and defense against parasites. Basophils, release histamine and heparin during allergic reactions. Monocytes, these differentiate into macrophages in tissues and are involved in phagocytosis. Platelets, small anucleate cells involved in blood clotting. The myeloid progenitor cells differentiate into precursor cells called myeloblasts, which give rise to granulocytes, and megakaryocytes, which give rise to platelets. B lymphoid lineage. Lymphopoiesis. Lymphoid progenitor cells give rise to B lymphocytes. B cells produce antibodies that fight infections. T lymphocytes. T cells regulate immune responses and directly attack infected cells. Natural killer NK cells play a role in the innate immune system by attacking infected or cancer cells. Lymphoid progenitor cells mature into different types of lymphocytes in the lymph nodes, spleen, and other lymphoid tissues. 4. Factors regulating hematopoiesis. Several cytokines, hormones, and growth factors regulate hematopoiesis. Erythropoietin EPO, a hormone primarily produced by the kidneys in response to low oxygen levels, hypoxia. It stimulates the production of erythrocytes, RBCs, in the bone marrow. Granulocyte colony stimulating factor, GCSF, stimulates the production of neutrophils. Granulocyte macrophage colony stimulating factor, GMCSF, stimulates the production of neutrophils, eosinophils, and monocytes. Thrombopoietin TPO stimulates the production of platelets by promoting the maturation of megakaryocytes. Interleukins ILs, a group of cytokines that influence the production of various immune cells, including lymphocytes. 5. Stages of erythropoiesis, RBC formation. The formation of RBCs is a critical part of myelopoiesis, and it involves several stages. Proerythroblast, the first primitive cell in the erythroid lineage. Basophilic erythroblast, cells that begin producing hemoglobin. Polychromatic erythroblast, these cells have a more abundant amount of hemoglobin, causing a grayish color. Orthochromatic erythroblast, a mature precursor of RBCs, where hemoglobin concentration is high. Reticulocyte, the last immature form of the RBC, which enters circulation before maturing into a full RBC. 6. Clinical relevance of hematopoiesis disorders of hematopoiesis can lead to several medical conditions. Anemia, a decrease in the number of RBCs or hemoglobin, resulting in insufficient oxygen transport. Leukemia, a type of cancer involving the uncontrolled proliferation of abnormal WBCs, often leading to a reduction in healthy blood cells. Thrombocytopenia, a low platelet count, leading to excessive bleeding and bruising. Polycythemia, an increase in RBCs, which can cause thickening of the blood and increase the risk of clots. 7. Previous year CSIR net questions 1. Hematopoiesis occurs primarily in which of the following? A. Liver. B. Kidney. C. Bone marrow. D. Spleen. Answer. C. Bone marrow. CSIR net Life Sciences, June 2019. 2. The hormone responsible for stimulating erythropoiesis is insulin. B. Thyroxine. C. Erythropoietin. D. Cortisol. Answer. C. Erythropoietin. CSIR net Life Sciences, December 2020. 3. Which of the following is a precursor of red blood cells in hematopoiesis? A. Proerythroblast. B. Myeloblast. C. Megakaryocyte. D. Monocyte. Answer. A proerythroblast. CSIR net Life Sciences, June 2018. 8. Conclusion. Hematopoiesis is a continuous process of blood cell production in the body, primarily occurring in the bone marrow. It is regulated by complex interplay of cytokines and growth factors that ensure proper differentiation and maturation of various blood cell types. Understanding the process of hematopoiesis is crucial for recognizing disorders related to blood cell formation, such as anemia, leukemia, and thrombocytopenia, which can significantly affect an individual's health. You said, formed elements. ChatGPT said, formed elements of blood. The formed elements of blood are the cellular components that make up a significant portion of blood volume. These elements include red blood cells, RBCs, white blood cells, WBCs, and platelets, thrombocytes. They are produced through the process of hematopoiesis, blood cell formation, in the bone marrow, although their functions and characteristics vary widely. 1. Red blood cells, erythrocytes, structure and characteristics. Shape. RBCs are biconcave discs with a flexible, flattened shape, which increases surface area for gas exchange and allows them to deform as they pass through small capillaries. Size. The average diameter of RBC is about 7 to 8 micrometers. Lifespan. Approximately 120 days in the bloodstream before being removed by the spleen and liver. No nucleus. Mature RBCs are enucleate, meaning they lack a nucleus, which allows more space for hemoglobin, the molecule responsible for oxygen and carbon dioxide transport. Function. RBCs are primarily responsible for oxygen transport from the lungs to tissues and carbon dioxide transport from tissues back to the lungs for exhalation. The protein hemoglobin within RBCs binds oxygen and carbon dioxide molecules, facilitating their transport. Clinical relevance. Anemia, a condition characterized by low RBC count or insufficient hemoglobin, leading to reduced oxygen carrying capacity. Polycythemia, a condition where there is an excessive number of RBCs, leading to increased blood viscosity and possible clotting. 2. White blood cells, leukocytes. WBCs are part of the immune system and are involved in defending the body against infections, foreign substances, and abnormal cells. There are two main categories of WBCs, granulocytes and agranulocytes. Agranulocytes, neutrophils. Structure. Neutrophils are the most abundant WBCs, constituting about 60–70% of the total leukocyte count. They have a multi-lobe nucleus and cytoplasmic granules. Function. Neutrophils are the body's first line of defense against bacterial infections and engage in phagocytosis, involving in destroying bacteria and debris. Eosinophils. Structure. Eosinophils have a violet nucleus and cytoplasmic granules that stain red with eosin. Function. They are involved in combating parasitic infections and modulating allergic reactions by releasing enzymes that break down the parasites or inflammatory mediators. Basophils. Structure. Basophils are the least common type of granulocyte and have a violet nucleus with large purple staining granules. Function. They release histamine, a vasodilator, and heparin, and anticoagulant during allergic reactions, leading to inflammation and increased blood flow to the affected area. Beta granulocytes, lymphocytes. Structure. Lymphocytes have a large, round nucleus and a thin rim of cytoplasm. They constitute about 20–25% of total WBCs. Function. Lymphocytes are primarily involved in adaptive immunity and include B cells, produce antibodies to target and neutralize pathogens. T cells, directly destroy infected or cancerous cells and assist in regulating immune responses. Natural killer NK cells, part of the innate immune system. They attack virus-infected and tumor cells. Monocytes. Structure. Monocytes are the largest type of WBC, with a large kidney-shaped nucleus. They make up about 3–8% of total WBCs. Function. Monocytes differentiate into macrophages in tissues, where they perform phagocytosis and play a key role in antigen presentation and activating other immune cells. Clinical relevance. Leukemia, a type of cancer involving the uncontrolled proliferation of abnormal WBCs, often leading to a decreased number of healthy blood cells. Leukopenia, a reduction in WBC count, making individuals more susceptible to infections. Leukocytosis, an elevated WBC count, often seen in response to infection, inflammation, or stress. 3. Platelets, thrombocytes. Structure. Platelets are small, anucleate cell fragments derived from megakaryocytes, large cells found in the bone marrow. They are about 2 to 4 micrometers in diameter and appear as small discs in circulation. Function. Platelets are critical in the process of blood clotting hemostasis. When a blood vessel is injured, platelets adhere to the damaged site, aggregate, and release substances that help form a clot to seal the wound. Platelets also release growth factors that promote tissue repair and regeneration. Lifespan. Platelets have a lifespan of 7 to 10 days before being removed by the spleen and liver. Clinical relevance. Thrombocytopenia, a condition characterized by low platelet count, which leads to increased risk of bleeding and difficulty in forming blood clots. Thrombocytosis, a condition of elevated platelet count, which can lead to an increased risk of clot formation, potentially causing strokes or heart attacks. 4. Clinical relevance of formed elements. The proper function of formed elements is crucial for maintaining overall health. Anemia, a condition where there is a reduction in the number of RBCs or insufficient hemoglobin, impairing oxygen delivery. Leukemia, a cancer of blood cells that results in abnormal proliferation of WBCs. Hemophilia, a genetic disorder where platelets are not functioning properly, leading to excessive bleeding. Infections and inflammatory diseases. An imbalance in WBC count can indicate the presence of infections, inflammation, or immune system disorders. 5. Previous year CSIR net questions. 1. Which of the following cells are responsible for producing antibodies? A. B lymphocytes. B T lymphocytes. C neutrophils. D monocytes. Answer. A B lymphocytes. CSIR net Life Sciences, December 2020. 2. The major function of platelets in the blood is to fight infections. B carry oxygen. C form blood clots. D transport nutrients. Answer. C form blood clots. CSIR net Life Sciences, June 2019. 3. The most abundant type of white blood cell in the human blood is a basophils. B neutrophils. C monocytes. D lymphocytes. Answer. B neutrophils. CSIR net Life Sciences, June 2018. 6. Conclusion. The formed elements of blood, red blood cells, white blood cells, and platelets are essential for the proper functioning of the circulatory and immune systems. RBCs are crucial for oxygen transport, WBCs for immune defense, and platelets for clotting and wound healing. Understanding the production, function, and clinical relevance of these elements is vital for diagnosing and treating various blood disorders and diseases. You said, plasma function. ChatGPT said, plasma function. Plasma is a liquid component of blood, constituting approximately 55% of total blood volume. It is a yellowish fluid that serves as a medium for transporting various substances throughout the body. Plasma is composed mainly of water, about 90%, along with proteins, electrolytes, nutrients, waste products, and gases. Its role is vital in maintaining homeostasis, nutrient distribution, waste removal, and immune defense. Components of plasma and their functions: water, 90%. Transport medium. Water is the primary solvent in plasma, facilitating the transport of various substances, including electrolytes, nutrients, hormones, and waste products. Temperature regulation. Water helps in maintaining the body's temperature by absorbing and redistributing heat. It plays a critical role in the regulation of body temperature, ensuring stability during fluctuations. Plasma proteins 7-8%. Plasma proteins are essential for various physiological processes. They are primarily produced by the liver and play crucial roles in maintaining osmotic pressure, immune response, and clotting. Albumins. Function. Albumins are the most abundant plasma proteins. They help maintain oncotic pressure, which prevents excessive fluid loss from blood vessels into surrounding tissues. Albumins also act as transporters for substances like fatty acids, hormones, and bilirubin. Globulins. Function. Globulins are involved in immune defense as antibodies or immunoglobulins and also transport lipids and fat-soluble vitamins. They are classified into alpha, beta, and gamma globulins. Alpha and beta globulins. These transport lipids, metal ions, and hormones and also play roles in clotting. Gamma globulins, immunoglobulins. These are antibodies involved in the body's defense against pathogens. Fibrinogen. Function. Fibrinogen is a key protein in the blood clotting process. Upon injury to blood vessels, fibrinogen is converted into fibrin, forming a mesh-like structure that helps in the formation of a blood clot to prevent excessive bleeding. Electrolytes. Plasma contains various electrolytes, such as sodium, Now+, potassium, K+, calcium, Ca2+, magnesium, Mg2+, chloride, Cl, and bicarbonate HCO3. These electrolytes maintain osmotic balance, regulate pH levels, and are critical for the proper function of muscles and nerves. Sodium and chloride, major contributors to osmotic pressure, fluid balance, and nerve transmission. Bicarbonate plays a significant role in maintaining the body's acid-base balance pH homeostasis. Potassium and calcium, essential for muscle contraction and nerve impulse transmission. Nutrients. Plasma transports essential nutrients such as glucose, amino acids, lipids, and vitamins to cells for energy production, growth, and repair. These nutrients are absorbed from the digestive tract and delivered to various organs and tissues. Glucose, the primary energy source for cells. Amino acids, building blocks for protein synthesis. Lipids, vital for cell membrane structure and energy storage. Vitamins and minerals, facilitate various biochemical reactions in the body. Waste products. Plasma also carries waste products produced by metabolism to the kidneys, liver, and lungs for excretion. Some examples include urea, a byproduct of protein metabolism, excreted by the kidneys. Carbon dioxide, CO2, a waste product of cellular respiration, transported in plasma mainly as bicarbonate to the lungs for exhalation. Uric acid, produced from the breakdown of purines, excreted via the kidneys. Gases. Plasma also carries oxygen and carbon dioxide. Oxygen, bound to hemoglobin in RBCs, but a small amount is dissolved directly in plasma. Carbon dioxide, the majority is transported in the form of bicarbonate ions, HCO3, in plasma. Hormones. Plasma is a medium for transporting various hormones, e.g., insulin, cortisol, thyroid hormones, which regulate different physiological processes like metabolism, growth, and stress response. These hormones are secreted by endocrine glands and travel through the bloodstream to their target organs. Functions of plasma. Transport. Plasma serves as a transportation medium for nutrients, gases, waste products, hormones, and immune cells throughout the body. This ensures that cells receive the necessary substances for metabolism and growth while waste products are removed efficiently. Maintaining osmotic and acid-base balance. Plasma proteins, particularly albumins, help maintain oncotic pressure, which keeps the fluid in the blood vessels and prevents excessive loss into surrounding tissues. Electrolytes like sodium, potassium, and bicarbonate are crucial in maintaining pH homeostasis and fluid balance. Clotting mechanism. Fibrinogen, along with other clotting factors, plays a central role in the formation of blood clots during an injury. This helps in preventing blood loss and promoting wound healing. Immune response. Plasma contains immunoglobulins, antibodies, which are part of the body's immune defense system. These antibodies help neutralize foreign pathogens like bacteria, viruses, and toxins. Temperature regulation. Plasma helps in the regulation of body temperature by distributing heat produced by metabolic processes throughout the body. It can also adjust to heat or cold conditions to maintain homeostasis. Nutrient and waste exchange. Plasma facilitates the exchange of nutrients and waste products between the blood and tissues. Nutrients are delivered to cells, and waste products like urea and CO2 are carried to organs like the kidneys and lungs for elimination. Previous year CSIR net questions 1. The most abundant plasma protein in human blood is a fibrinogen. B albumin, C globulin, D hemoglobin. Answer. B albumin, CSIR net Life Sciences, June 2018. 2. Plasma proteins play an important role in oxygen transport. B clotting mechanism, C regulation of body temperature, D both B and C. Answer. D both B and C. CSIR net Life Sciences, December 2020. 3. Which of the following is not a function of plasma proteins? A transport of lipids. B regulation of blood pressure, C transport of gases, D maintenance of osmotic pressure. Answer. C transport of gases, CSIR net Life Sciences, June 2019. Conclusion. Plasma plays a crucial role in the overall functioning of the circulatory system by maintaining fluid balance, transporting nutrients and products, supporting immune functions, regulating blood clotting, and maintaining homeostasis in the body. Understanding the composition and function of plasma is essential for studying blood physiology and its relation to various health conditions and diseases. You said blood volume. ChatGPT said blood volume. Blood volume refers to the total volume of blood in the circulatory system of an individual. It is a critical physiological parameter that influences cardiovascular function, oxygen delivery, and waste removal. The total blood volume is distributed across various components of the body and fluctuates based on factors such as age, sex, body size, and health condition. Normal blood volume. For an average adult, the total blood volume is approximately 7-8% of body weight. In terms of actual volume. For males, typically around 5 to 6 liters, approximately 70 milliliters per kilogram of body weight. For females, typically around 4.55 liters, approximately 65 milliliters per kilogram of body weight. Factors affecting blood volume. Body size. Larger individuals generally have a higher blood volume due to greater body mass. Sex. Males typically have a higher blood volume than females, largely due to differences in body composition, muscle mass, and fat. Age. Children have a higher blood volume per unit of body weight compared to adults. Health conditions. Conditions like dehydration, bleeding, or certain diseases can reduce blood volume, while states like pregnancy can increase it. Blood volume distribution. Blood is distributed across various components of the circulatory system. Plasma. Approximately 55% of total blood volume. Plasma is the liquid portion of the blood that carries nutrients, hormones, and waste products. Foreign elements. The remaining 45% of blood volume consists of foreign elements. Red blood cells, RBCs, approximately 40-45% of blood volume. RBCs are responsible for oxygen and carbon dioxide transport. White blood cells, WBCs, less than 1% of blood volume. WBCs play a crucial role in immune defense. Platelets, less than 1% of blood volume. Platelets are essential for clot formation and wound healing. Regulation of blood volume. Blood volume is tightly regulated by the body through mechanisms that involve the kidneys, hormones, and the cardiovascular system. Some of the key regulatory factors include renin-angiotensin-aldosterone system, ROS. The kidneys release renin in response to low blood pressure or low sodium levels, which activates the renin-angiotensin-aldosterone system. This system increases sodium reabsorption in the kidneys, leading to water retention, which increases blood volume. Antidiuretic hormone, ADH. Released by the pituitary gland, ADH promotes water reabsorption in the kidneys, leading to increased blood volume. ADH release is triggered by high blood osmolality, i.e., dehydration. Atrial natriuretic peptide, ANP. ANP is released by the heart in response to increased blood volume or pressure. It promotes the excretion of sodium and water, reducing blood volume. Sympathetic nervous system. The sympathetic nervous system regulates blood volume through vasoconstriction and by influencing kidney function. It can rapidly adjust blood volume in response to stress or changes in blood pressure. Functions of blood volume. Oxygen and nutrient transport. Blood volume ensures that there is sufficient blood flow to all tissues, facilitating the delivery of oxygen, nutrients, and hormones to cells throughout the body. Waste removal. Blood helps in the removal of metabolic waste products, including carbon dioxide and urea, which are transported to organs such as the lungs and kidneys for excretion. Maintaining blood pressure. Adequate blood volume is essential for maintaining blood pressure. Low blood volume hypovolemia can lead to a drop in blood pressure, while excessive blood volume hypervolemia can result in hypertension. Temperature regulation. Blood volume plays a role in regulating body temperature. Blood helps distribute heat throughout the body and assists in cooling mechanisms through the skin. Changes in blood volume and related conditions. Hypovolemia. Low blood volume. Caused by conditions such as dehydration, hemorrhage, or shock. Hypovolemia leads to reduced cardiac output, low blood pressure, and inadequate perfusion of organs and tissues. Symptoms include dizziness, weakness, rapid heartbeat, and confusion. Hypervolemia. High blood volume. Occurs in conditions such as kidney failure, heart failure, or excessive sodium retention. It can lead to edema, swelling, and high blood pressure, as well as complications such as pulmonary edema, where excess fluid accumulates in the lungs. Pregnancy. Blood volume increases by about 30–50% during pregnancy to meet the increased metabolic demands of the mother and developing fetus. This increase is due to the expansion of plasma volume, which helps support uterine and placental function. Previous year CSIR net questions 1. The blood volume in a healthy adult male is approximately 8.4 liters. B5 liters, C6 liters, D7 liters. Answer. B5 liters, CSIR net Life Sciences, June 2018. 2. Which of the following hormones is primarily involved in the regulation of blood volume? A. Insulin. B. Adrenaline. C. Aldosterone. D. Thyroxine. Answer. C. Aldosterone. CSIR net Life Sciences, December 2020. 3. In the case of hypovolemia, which of the following is most likely to occur? A. Increased blood pressure. B. Decreased cardiac output. C. Increased urine production. D. Decreased sodium retention. Answer. B. Decreased cardiac output. CSIR net Life Sciences, June 2019. Conclusion. Blood volume is a crucial parameter for maintaining physiological balance in the body. It supports vital functions such as oxygen and nutrient transport, waste elimination, blood pressure regulation, and temperature control. BR. Blood corpuscles, or blood cells, are the cellular components of blood responsible for various functions such as transporting gases, fighting infections, and aiding in clotting. Blood corpuscles can be categorized into three main types: red blood cells (RBCs), white blood cells (WBCs), and platelets. Each type has distinct roles in maintaining the body's health and physiological balance. 1. Red blood cells (RBCs), erythrocyte structure. Shape: RBCs are biconcave discs, which provide a large surface area for gas exchange. Size: the average diameter is about 7 to 8 micrometers. Lifespan: typically 120 days. Function: the primary function of RBCs is the transport of oxygen from the lungs to tissues and the return of carbon dioxide from the tissues to the lungs for exhalation. RBCs contain hemoglobin, a protein that binds to oxygen molecules in the lungs and releases them in tissues with lower oxygen concentration. Hemoglobin also helps in the transport of carbon dioxide, where it binds CO2 and carries it back to the lungs, where it is expelled. Formation: erythropoiesis. RBCs are produced in the red bone marrow through a process called erythropoiesis. The production is regulated by the hormone erythropoietin, which is released by the kidneys in response to low oxygen levels in the blood. Disposal: older damaged RBCs are broken down in the spleen and liver, where hemoglobin is metabolized and the iron is recycled. 2. White blood cells (WBCs), leukocyte structure. WBCs are larger than RBCs and have a nucleus, unlike RBCs which are enucleate. They are usually colorless because they lack hemoglobin. WBCs are present in much smaller quantities compared to RBCs but are crucial for immune functions. Types of WBCs and their functions: neutrophils. Make up 55–70% of the total WBC count. These cells are the first line of defense during an infection and are phagocytic, engulf and digest pathogens, such as bacteria. Lymphs comprise 20–40% of the WBC population. B cells produce antibodies that recognize specific antigens, while T cells are involved in directly attacking infected cells or regulating the immune response. They are crucial for adaptive immunity. Monocytes represent 2–8% of the WBCs. They differentiate into macrophages in tissues, which are also phagocytic and play a role in immune response and inflammation. Eosinophils account for 1–4% of WBCs. They are involved in allergic reactions and parasitic infections. Basophils represent less than 1% of WBCs. These cells release histamine during allergic responses and contribute to inflammation. Function: the primary function of WBCs is defense against infections. They are involved in the body's immune response, identifying and neutralizing pathogens like bacteria, viruses, and fungi. Formation: leukopoiesis. WBCs are produced in the bone marrow, with some types also originating in the lymph nodes and spleen. Their production is influenced by various cytokines and growth factors such as colony-stimulating factors. 3. Platelets. Thrombocyte structure. Platelets are cell fragments derived from larger cells called megakaryocytes in the bone marrow. They are small, irregularly shaped, and lack a nucleus. Function: platelets are primarily involved in blood clotting hemostasis. They form a plug at the site of a blood vessel injury and release clotting factors to aid in the formation of a fibrin clot, which prevents excessive blood loss. Mechanism of clotting: when a blood vessel is damaged, platelets adhere to the exposed collagen fibers at the injury site. They release ADP, adenosine diphosphate, thromboxane E2, and other factors that activate nearby platelets. Platelets aggregate to form a platelet plug. The clotting cascade is activated, involving proteins like fibrinogen, which are converted into fibrin threads that stabilize the clot. Formation: thrombopoiesis. Platelets are produced in the bone marrow from megakaryocytes under the influence of the hormone thrombopoietin, primarily produced by the liver. 4. Blood cell counts and their significance. Red blood cells. Normal counts range from 4.7 to 6.1 million cells per microliter of blood in men and 4.2 to 5.4 million in women. White blood cells. Normal count ranges from 4,000 to 11,000 cells per microliter of blood. Platelets. Normal count ranges from 150,000 to 450,000 platelets per microliter of blood. Abnormal counts of any blood cell type can indicate various health conditions. Anemia, low RBC count, results in fatigue and weakness. Leukocytosis, high WBC count, may indicate infection or inflammation. Thrombocytopenia, low platelet count, increases the risk of bleeding. 5. Previous year CSIR net questions. 1. Which of the following blood components is primarily responsible for the immune defense of the body? A. Platelets. B. White blood cells. C. Red blood cells. D. Plasma proteins. Answer. B. White blood cells. CSIR net Life Sciences, June 2020. 2. What is the primary function of platelets in the blood? A. Oxygen transport. B. Immune response. C. Blood clotting. D. Nutrient transport. Answer. C. Blood clotting. CSIR net Life Sciences, December 2018. 3. The primary function of red blood cells is 2. A. Transport carbon dioxide. B. Transport oxygen. C. Fight infections. D. Form blood clots. Answer. B. Transport oxygen. CSIR net Life Sciences, June 2019. 6. Conclusion. Blood corpuscles, including red blood cells, white blood cells, and platelets, perform critical functions for survival. RBCs are responsible for transporting oxygen. WBCs protect against infections, and platelets ensure proper blood clotting. A thorough understanding of these cells and their functions is crucial for studying animal physiology and the body's defense mechanisms. Any abnormalities in blood corpuscles can lead to serious medical conditions, underlying their importance in maintaining health and homeostasis. You said. Hemopoiesis. ChatGPT said. Hematopoiesis, the formation of blood cells. Hematopoiesis, also known as hematopoiesis, is the process through which all the blood cells, including red blood cells, RBCs, white blood cells, WBCs, and platelets, are produced. This process primarily occurs in the bone marrow but can also take place in other organs like the liver and spleen under certain conditions, especially during fetal development or in pathological states. Hematopoiesis is regulated by a complex network of growth factors, hormones, and cytokines that ensure the proper formation, maturation, and differentiation of blood cells. 1. Site of hematopoiesis. Fetal development. In early fetal life, up to about 2 to 3 months, hematopoiesis takes place in the yolk sac. As development progresses, it shifts to the liver and spleen, and later, after birth, the bone marrow becomes the primary site. Adult life. In adults, hematopoiesis primarily occurs in the red bone marrow, located in the flat bones, such as the sternum, ribs, pelvis, and the ends of long bones like the femur. 2. Hematopoietic stem cells, HSCs. Pluripotent stem cells. The starting point for all blood cells is a hematopoietic stem cell, HSC, a multipotent stem cell found in the bone marrow. These HSCs are capable of differentiating into all types of blood cells. HSCs are self-renewing, meaning they can produce more HSCs, ensuring a continuous supply of new blood cells throughout life. Differentiation. HSCs give rise to 2 primary progenitor cell lines, myeloid progenitors and lymphoid progenitors. These progenitors further differentiate into various blood cell types under the influence of specific growth factors and cytokines. 3. Stages of hematopoiesis. Hematopoiesis occurs through a series of stages, with progenitor cells progressively differentiating into mature blood cells. A myeloid lineage. Myelopoiesis. Myeloid progenitor cells give rise to erythrocytes, RBCs, red blood cells that transport oxygen and carbon dioxide. Granulocytes, white blood cells involved in immune defense. These include Neutrophils, the most abundant WBCs involved in phagocytosis of bacteria. Eosinophils, involved in allergic reactions and defense against parasites. Basophils, release histamine and heparin during allergic reactions. Monocytes, these differentiate into macrophages in tissues and are involved in phagocytosis. Platelets, small anucleate cells involved in blood clotting. The myeloid progenitor cells differentiate into precursor cells called myeloblasts, which give rise to granulocytes, and megakaryocytes, which give rise to platelets. B lymphoid lineage lymphobiosis, lymphoid progenitor cells give rise to B lymphocytes, B cells produce antibodies that fight infections. T lymphocytes, T cells regulate immune responses and directly attack infected cells. Natural killer NK cells play a role in the innate immune system by attacking infected or cancer cells. Lymphoid progenitor cells mature into different types of lymphocytes in the lymph nodes, spleen, and other lymphoid tissues. 4. Factors regulating hematopoiesis. Several cytokines, hormones, and growth factors regulate hematopoiesis. Erythropoietin EPO, a hormone primarily produced by the kidneys in response to low oxygen levels, hypoxia. It stimulates the production of erythrocytes, RBCs, in the bone marrow. Granulocyte colony stimulating factor, GCSF, stimulates the production of neutrophils. Granulocyte macrophage colony stimulating factor, GM-CSF, stimulates the production of neutrophils, eosinophils, and monocytes. Thrombopoietin TPO stimulates the production of platelets by promoting the maturation of megakaryocytes. Interleukins ILs, a group of cytokines that influence the production of various immune cells, including lymphocytes. 5. Stages of erythropoiesis, RBC formation. The formation of RBCs is a critical part of myelopoiesis, and it involves several stages. Proerythroblast, the first committed cell in the erythroid lineage. Basophilic erythroblast, cells that begin producing hemoglobin. Polychromatic erythroblast, these cells have a more abundant amount of hemoglobin, causing a grayish color. Orthochromatic erythroblast, a mature precursor of RBCs, where hemoglobin concentration is high. Reticulocyte, the last immature form of the RBC, which enters circulation before maturing into a full RBC. 6. Clinical relevance of hematopoiesis disorders. Hematopoiesis can lead to several medical conditions. Anemia, a decrease in the number of RBCs or hemoglobin, resulting in insufficient oxygen transport. Leukemia, a type of cancer involving the uncontrolled proliferation of abnormal WBCs, often leading to a reduction in healthy blood cells. Thrombocytopenia, a low platelet count, leading to excessive bleeding and bruising. Polycythemia, an increase in RBCs, which can cause thickening of the blood and increase the risk of clots. 7. Previous year CSIR net questions. 1. Hematopoiesis occurs primarily in which of the following? A. Liver. B. Kidney. C. Bone marrow. D. Spleen. Answer. C. Bone marrow. CSIR net Life Sciences, June 2019. 2. The hormone responsible for stimulating erythropoiesis is insulin. B. Thyroxine. C. Erythropoietin. D. Cortisol. Answer. C. Erythropoietin. CSIR net Life Sciences, December 2020. 3. Which of the following is the precursor of red blood cells in hematopoiesis? A. Proerythroblast. B. Myeloblast. C. Megakaryocyte. D. Monocyte. Answer. A proerythroblast. CSIR net Life Sciences, June 2018. 8. Conclusion. Hematopoiesis is a continuous process of blood cell production in the body, primarily occurring in the bone marrow. It is regulated by a complex interplay of cytokines and growth factors that ensure proper differentiation and maturation of various blood cell types. Understanding the process of hematopoiesis is crucial for recognizing disorders related to blood cell formation, such as anemia, leukemia, and thrombocytopenia, which can significantly affect an individual's health. You said, formed elements. ChatGPT said, formed elements of blood. The formed elements of blood are the cellular components that make up a significant portion of blood volume. These elements include red blood cells, RBCs, white blood cells, WBCs, and platelets, thrombocytes. They are produced through the process of hematopoiesis, blood cell formation, in the bone marrow, although their functions and characteristics vary widely. 1. Red blood cells, erythrocytes, structure and characteristics. Shape. RBCs are biconcave discs with a flexible, flattened shape, which increases surface area for gas exchange and allows them to deform as they pass through small capillaries. Size. The average diameter of the RBC is about 7 to 8 micrometers. Lifespan. Approximately 120 days in the bloodstream before being removed by the spleen and liver. No nucleus. Mature RBCs are enucleate, meaning they lack a nucleus, which allows more space for hemoglobin, the molecule responsible for oxygen and carbon dioxide transport. Function. RBCs are primarily responsible for oxygen transport from the lungs to tissues and carbon dioxide transport from tissues back to the lungs for exhalation. The protein hemoglobin within RBCs binds oxygen and carbon dioxide molecules, facilitating their transport. Clinical relevance. Anemia, a condition characterized by low RBC count or insufficient hemoglobin, leading to reduced oxygen carrying capacity. Polycythemia, a condition where there is an excessive number of RBCs, leading to increased blood viscosity and possible clotting. 2. White blood cells, leukocytes. WBCs are part of the immune system and are involved in defending the body against infections, foreign substances, and abnormal cells. There are two main categories of WBCs, granulocytes and agranulocytes. A granulocytes, neutrophils. Structure. Neutrophils are the most abundant WBCs, constituting about 60-70% of the total leukocyte count. They have a multi-lobe nucleus and cytoplasmic granules. Function. Neutrophils are the body's first line of defense against bacterial infections and engage in phagocytosis, involving in destroying bacteria and debris. Eosinophils. Structure. Eosinophils have a bilobed nucleus and cytoplasmic granules that stain red with eosin. Function. They are involved in combating parasitic infections and modulating allergic reactions by releasing enzymes that break down the parasites or inflammatory mediators. Bales. Structure. Basophils are the least common type of granulocyte and have a bilobed nucleus with large purple staining granules. Function. They release histamine, a vasodilator, and heparin, and anticoagulant during allergic reactions, leading to inflammation and increased blood flow to the affected area. Beta granulocytes, lymphocytes. Structure. Lymphocytes have a large, round nucleus and a thin rim of cytoplasm. They constitute about 20-25% of total WBCs. Function. Lymphocytes are primarily involved in adaptive immunity and include B cells, produce antibodies to target and neutralize pathogens. T cells, directly destroy infected or cancerous cells and assist in regulating immune responses. Natural killer NK cells, part of the innate immune system. They attack virus-infected and tumor cells. Monocytes. Structure. Monocytes are the largest type of WBC, with a large kidney-shaped nucleus. They make up about 3-8% of total WBCs. Function. Monocytes differentiate into macrophages in tissues, where they perform phagocytosis and play a key role in antigen presentation and activating other immune cells. Clinical relevance. Leukemia, a type of cancer involving the uncontrolled proliferation of abnormal WBCs, often leading to a decreased number of healthy blood cells. Leukopenia, a reduction in WBC count, making individuals more susceptible to infections. Leukocytosis, an elevated WBC count, often seen in response to infection, inflammation, or stress. 3. Platelets, thrombocytes. Structure. Platelets are small, anucleate cell fragments derived from megakaryocytes, large cells found in the bone marrow. They are about 2 to 4 micrometers in diameter and appear as small discs in circulation. Function. Platelets are critical in the process of blood clotting hemostasis. When a blood vessel is injured, platelets adhere to the damaged site, aggregate, and release substances that help form a clot to seal the wound. Platelets also release growth factors that promote tissue repair and regeneration. Lifespan. Platelets have a lifespan of 7 to 10 days before being removed by the spleen and liver. Clinical relevance. Thrombocytopenia, a condition characterized by low platelet count, which leads to increased risk of bleeding and difficulty in forming blood clots. Thrombocytosis, a condition of elevated platelet count, which can lead to an increased risk of clot formation, potentially causing strokes or heart attacks. 4. Clinical relevance of formed elements. The proper function of formed elements is crucial for maintaining overall health. Anemia, a condition where there is a reduction in the number of RBCs or insufficient hemoglobin, impairing oxygen delivery. Leukemia, a cancer of blood cells that results in abnormal proliferation of WBCs. Hemophilia, a genetic disorder where platelets are not functioning properly, leading to excessive bleeding. Infections and inflammatory diseases. An imbalance in WBC count can indicate the presence of infections, inflammation, or immune system disorders. 5. Previous year CSIR net questions. 1. Which of the following cells are responsible for producing antibodies? A. B. Lymphocytes. BT lymphocytes C neutrophils D monocytes. Answer. AB lymphocytes CSIR Net Life Sciences December 2020. 2. The major function of platelets in the blood is 2. Of fighting infections. B carry oxygen C form blood clots D transport nutrients. Answer. C form blood clots CSIR Net Life Sciences June 2019. 3. The most abundant type of white blood cell in the human blood is of basophils. B neutrophils C monocytes D lymphocytes. Answer. B neutrophils CSIR Net Life Sciences June 2018. 6. Conclusion. The formed elements of blood, red blood cells, white blood cells, and platelets are essential for the proper functioning of the circulatory and immune systems. RBCs are crucial for oxygen transport, WBCs for immune defense, and platelets for clotting and wound healing. Understanding the production, function, and clinical relevance of these elements is vital for diagnosing and treating various blood disorders and diseases. You said, plasma function. ChatGPT said, plasma function. Plasma is a liquid component of blood, constituting approximately 55% of total blood volume. It is a yellowish fluid that serves as a medium for transporting various substances throughout the body. Plasma is composed mainly of water, about 90%, along with proteins, electrolytes, nutrients, waste products, and gases. Its role is vital in maintaining homeostasis, nutrient distribution, waste removal, and immune defense. Components of plasma and their functions: water, 90%. Transport medium. Water is the primary solvent in plasma, facilitating the transport of various substances, including electrolytes, nutrients, hormones, and waste products. Temperature regulation. Water helps in maintaining the body's temperature by absorbing and redistributing heat. It plays a critical role in the regulation of body temperature, ensuring stability during fluctuations. Plasma proteins, 7-8%. Plasma proteins are essential for various physiological processes. They are primarily produced by the liver and play crucial roles in maintaining osmotic pressure, immune response, and clotting. Albumins. Function. Albumins are the most abundant plasma proteins. They help maintain oncotic pressure, which prevents excessive fluid loss from blood vessels into surrounding tissues. Albumins also act as transporters for substances like fatty acids, hormones, and bilirubin. Globulins. Function. Globulins are involved in immune defense as antibodies or immunoglobulins and also transport lipids and fat-soluble vitamins. They are classified into alpha, beta, and gamma globulins. Alpha and beta globulins. These transport lipids, metal ions, and hormones, and also play roles in clotting. Gamma globulins, immunoglobulins. These are antibodies involved in the body's defense against pathogens. Fibrinogen. Function. Fibrinogen is a key protein in the blood clotting process. Upon injury to blood vessels, fibrinogen is converted into fibrin, forming a mesh-like structure that helps in the formation of a blood clot to prevent excessive bleeding. Electrolytes. Plasma contains various electrolytes, such as sodium, Now+, potassium, K+, calcium, Ca2+, magnesium, Mg2+, chloride, Cl, and bicarbonate HCO3. These electrolytes maintain osmotic balance, regulate pH levels, and are critical for the proper function of muscles and nerves. Sodium and chloride, major contributors to osmotic pressure, fluid balance, and nerve transmission. Bicarbonate plays a significant role in maintaining the body's acid-base balance, pH homeostasis. Potassium and calcium, essential for muscle contraction and nerve impulse transmission. Nutrients. Plasma transports essential nutrients such as glucose, amino acids, lipids, and vitamins to cells for energy production, growth, and repair. These nutrients are absorbed from the digestive tract and delivered to various organs and tissues. Glucose, the primary energy source for cells. Amino acids, building blocks for protein synthesis. Lipids, vital for cell membrane structure and energy storage. Vitamins and minerals, facilitate various biochemical reactions in the body. Waste products. Plasma also carries waste products produced by metabolism to the kidneys, liver, and lungs for excretion. Some examples include urea, a byproduct of protein metabolism, excreted by the kidneys. Carbon dioxide, CO2, a waste product of cellular respiration, transported in plasma mainly as bicarbonate to the lungs for exhalation. Uric acid, produced from the breakdown of purines, excreted via the kidneys. Gases. Plasma also carries oxygen and carbon dioxide. Oxygen, bound to hemoglobin and RBCs, but a small amount is dissolved directly in plasma. Carbon dioxide, the majority is transported in the form of bicarbonate ions, HCO3, in plasma. Hormones. Plasma is a medium for transporting various hormones, e.g., insulin, cortisol, thyroid hormones, which regulate different physiological processes like metabolism, growth, and stress response. These hormones are secreted by endocrine glands and travel through the bloodstream to their target organs. Functions of plasma. Transport. Plasma serves as a transportation medium for nutrients, gases, waste products, hormones, and immune cells throughout the body. This ensures that cells receive the necessary substances for metabolism and growth while waste products are removed efficiently. Maintaining osmotic and acid-base balance. Plasma proteins, particularly albumins, help maintain oncotic pressure, which keeps the fluid in the blood vessels and prevents excessive loss into surrounding tissues. Electrolytes like sodium, potassium, and bicarbonate are crucial in maintaining pH homeostasis and fluid balance. Clotting mechanism. Fibrinogen, along with other clotting factors, plays a central role in the formation of blood clots during an injury. This helps in preventing blood loss and promoting wound healing. Immune response. Plasma contains immunoglobulins, antibodies, which are part of the body's immune defense system. These antibodies help neutralize foreign pathogens like bacteria, viruses, and toxins. Temperature regulation. Plasma helps in the regulation of body temperature by distributing heat produced by metabolic processes throughout the body. It can also adjust to heat or cold conditions to maintain homeostasis. Nutrient and waste exchange. Plasma facilitates the exchange of nutrients and waste products between the blood and tissues. Nutrients are delivered to cells, and waste products like urea and CO2 are carried to organs like the kidneys and lungs for elimination. Previous year CSIR net questions 1. The most abundant plasma protein in human blood is of fibrinogen. B albumin C globulin D hemoglobin. Answer. B albumin CSIR net life sciences June 2018. 2. Plasma proteins play an important role in oxygen transport. B clotting mechanism. C regulation of body temperature. D both B and C. Answer. D both B and C CSIR net life sciences December 2020. 3. Which of the following is not a function of plasma proteins? A transport of lipids. B regulation of blood pressure. C transport of gases. D maintenance of osmotic pressure. Answer. C transport of gases. CSIR net life sciences June 2019. Conclusion. Plasma plays a crucial role in the overall functioning of the circulatory system by maintaining fluid balance, transporting nutrients and waste products, supporting immune functions, regulating blood clotting, and maintaining homeostasis in the body. Understanding the composition and function of plasma is essential for studying blood physiology and its relation to various health conditions and diseases. You said, blood volume. ChatGPT said, blood volume. Blood volume refers to the total volume of blood in the circulatory system of an individual. It is a critical physiological parameter that influences cardiovascular function, oxygen delivery, and waste removal. The total blood volume is distributed across various components of the body and fluctuates based on factors such as age, sex, body size, and health condition. Normal blood volume. For an average adult, the total blood volume is approximately 7-8% of body weight. In terms of actual volume. For males, typically around 5 to 6 liters, approximately 70 milliliters per kilogram of body weight. For females, typically around 4.55 liters, approximately 65 milliliters per kilogram of body weight. Factors affecting blood volume. Body size. Larger individuals generally have a higher blood volume due to greater body mass. Sex. Males typically have a higher blood volume than females, largely due to differences in body composition, muscle mass, and fat. Age. Children have a higher blood volume per unit of body weight compared to adults. Health conditions. Conditions like dehydration, bleeding, or certain diseases can reduce blood volume, while states like pregnancy can increase it. Blood volume distribution. Blood is distributed across various components of the circulatory system. Plasma. Approximately 55% of total blood volume. Plasma is a liquid portion of the blood that carries nutrients, hormones, and waste products. Foreign elements. The remaining 45% of blood volume consists of foreign elements. Red blood cells, RBCs, approximately 40-45% of blood volume. RBCs are responsible for oxygen and carbon dioxide transport. White blood cells, WBCs, less than 1% of blood volume. WBCs play a crucial role in immune defense. Platelets, less than 1% of blood volume. Platelets are essential for clot formation and wound healing. Regulation of blood volume. Blood volume is tightly regulated by the body through mechanisms that involve the kidneys, hormones, and the cardiovascular system. Some of the key regulatory factors include renin-angiotensin-aldosterone system (ROS). The kidneys release renin in response to low blood pressure or low sodium levels, which activates the renin-angiotensin-aldosterone system. This system increases sodium reabsorption in the kidneys, leading to water retention, which increases blood volume. Antidiuretic hormone, ADH. Released by the pituitary gland, ADH promotes water reabsorption in the kidneys, leading to increased blood volume. ADH release is triggered by high blood osmolality, i.e., dehydration. Atrial natriuretic peptide, ANP. ANP is released by the heart in response to increased blood volume or pressure. It promotes the excretion of sodium and water, reducing blood volume. Sympathetic nervous system. The sympathetic nervous system regulates blood volume through vasoconstriction and by influencing kidney function. It can rapidly adjust blood volume in response to stress or changes in blood pressure. Functions of blood volume. Oxygen and nutrient transport. Blood volume ensures that there is sufficient blood flow to all tissues, facilitating the delivery of oxygen, nutrients, and hormones to cells throughout the body. Waste removal. Blood helps in the removal of metabolic waste products, including carbon dioxide and urea, which are transported to organs such as the lungs and kidneys for excretion. Maintaining blood pressure. Adequate blood volume is essential for maintaining blood pressure. Low blood volume hypovolemia can lead to a drop in blood pressure, while excessive blood volume hypervolemia can result in hypertension. Temperature regulation. Blood volume plays a role in regulating body temperature. Blood helps distribute heat throughout the body and assists in cooling mechanisms through the skin. Changes in blood volume and related conditions. Hypovolemia, low blood volume. Caused by conditions such as dehydration, hemorrhage, or shock. Hypovolemia leads to reduced cardiac output, low blood pressure, and inadequate perfusion of organs and tissues. Symptoms include dizziness, weakness, rapid heartbeat, and confusion. Hypervolemia, high blood volume. Occurs in conditions such as kidney failure, heart failure, or excessive sodium retention. It can lead to edema, swelling, and high blood pressure, as well as complications such as pulmonary edema, where excess fluid accumulates in the lungs. Pregnancy. Blood volume increases by about 30–50% during pregnancy to meet the increased metabolic demands of the mother and developing fetus. This increase is due to the expansion of plasma volume, which helps support uterine and placental function. Previous year CSIR net questions 1. The blood volume in a healthy adult male is approximately 8.4 liters. B5 liters, C6 liters, D7 liters. Answer. B5 liters. CSIR net life sciences, June 2018. 2. Which of the following hormones is primarily involved in the regulation of blood volume? A. Insulin. B. Adrenaline. C. Aldosterone. D. Thyroxine. Answer. C. Aldosterone. CSIR net life sciences, December 2020. 3. In the case of hypovolemia, which of the following is most likely to occur? A. Increased blood pressure. B. Decreased cardiac output. C. Increased urine production. D. Decreased sodium retention. Answer. B. Decreased cardiac output. CSIR net life sciences, June 2019. Conclusion. Blood volume is a crucial parameter for maintaining physiological balance in the body. It supports vital functions such as oxygen and nutrient transport, waste elimination, blood pressure regulation, and temperature control. The regulation of blood volume involves a complex interaction of hormones, the kidneys, and the cardiovascular system. Understanding these mechanisms is essential for diagnosing and managing various health conditions related to blood volume imbalances. You said. Blood volume regulation. ChatGPT said. Blood volume regulation. Blood volume regulation is a critical physiological process that ensures homeostasis in the body. It involves the precise control of blood volume to maintain blood pressure, organ perfusion, and fluid balance within the circulatory system. This regulation is carried out through various mechanisms involving the kidneys, the cardiovascular system, and hormonal influences. Mechanisms involved in blood volume regulation: renin-angiotensin-aldosterone system (RAAS). The RAS is one of the key systems for regulating blood volume and blood pressure. It becomes activated when there is a decrease in blood flow to the kidneys, e.g., due to dehydration or hemorrhage. Renin release. In response to low blood pressure or sodium levels, specialized cells in the kidney juxtaglomerular cells release the enzyme renin. Angiotensinogen conversion. Renin acts on angiotensinogen, a plasma protein produced by the liver, converting it into angiotensin I. Angiotensin II formation. Angiotensin I is then converted to angiotensin II by the enzyme angiotensin converting enzyme based primarily in the lungs. Effects of angiotensin II. Vasoconstriction. Angiotensin II constricts blood vessels, increasing peripheral resistance and raising blood pressure. Aldosterone secretion. It stimulates the adrenal glands to secrete aldosterone, which promotes sodium and water retention in the kidneys, thereby increasing blood volume. ADH release. Angiotensin II also triggers the release of antidiuretic hormone, ADH, from the pituitary gland, which further aids in water retention by the kidneys. Antidiuretic hormone, ADH, vasopressin. ADH, also known as vasopressin, is another important hormone that regulates blood volume and water balance in the body. Synthesis and release. ADH is synthesized in the hypothalamus and stored in the posterior pituitary gland. It is released in response to increased blood osmolarity, dehydration, or low blood volume. Kidney function. ADH acts on the kidneys, specifically on the collecting ducts, increasing their permeability to water. This results in water reabsorption back into the bloodstream, which increases blood volume. Vasoconstriction. ADH also causes mild vasoconstriction, helping to raise blood pressure during periods of low blood volume. Atrial natriuretic peptide, ANP. ANP is a hormone that plays a counter-regulatory role to RAS and ADH in blood volume regulation. Release. ANP is released from the heart's atrial cells in response to increased blood volume or pressure, e.g., during fluid overload. Effects. Diuresis. ANP promotes the excretion of sodium and water by the kidneys, decreasing blood volume and lowering blood pressure. Vasodilation. It causes blood vessels to dilate, further lowering blood pressure. Inhibition of RAS. ANP inhibits the secretion of renin and aldosterone, which helps to reduce blood volume and pressure. Sympathetic nervous system, SNS. The SNS plays a significant role in short-term regulation of blood volume and blood pressure. Baroreceptor reflex. Baroreceptors located in the carotid sinuses and the aortic arch detect changes in blood pressure. In response to low blood pressure, the SNS is activated, which causes vasoconstriction and increased heart rate, thereby improving blood flow and increasing blood volume. Renal effects. The SNS can also stimulate the kidneys to retain sodium and water, contributing to the increase in blood volume. Kidney function and fluid balance. The kidneys play a central role in the long-term regulation of blood volume. They do so by filtering blood, reabsorbing water and solutes, and excreting excess fluids and waste products. Glomerular filtration rate (GFR). The kidneys adjust GFR in response to blood volume changes. Low blood volume leads to decreased GFR to conserve water and sodium. Tubular reabsorption. In the renal tubules, sodium, water, and other solutes are reabsorbed into the bloodstream under the influence of hormones like aldosterone and ADH. This process helps to restore blood volume. Erythropoiesis. The kidneys also produce erythropoietin in response to low blood volume and oxygen levels, stimulating the production of red blood cells to increase oxygen delivery to tissues. Fluid shifts between compartments. The body's extracellular fluid is divided into two major compartments: the intravascular space inside blood vessels and the interstitial space between cells. Blood volume can be influenced by the movement of water between these compartments. Capillary exchange. Water moves between the intravascular and interstitial compartments based on the balance of hydrostatic and osmotic pressures. For example, when blood volume decreases, fluid can shift from the interstitial space into the blood vessels to help restore blood volume. Lymphatic system. The lymphatic system helps to return excess fluid from the tissues back into the circulatory system, contributing to blood volume regulation. Role of the lymphatic system. The lymphatic system is involved in the regulation of blood volume by returning interstitial fluid, which contains proteins and water, back to the blood circulation. This helps to prevent edema, fluid accumulation in tissues, and maintains the proper volume of blood in the circulatory system. Regulation in response to blood loss or hemorrhage. In the case of blood loss, mechanisms to restore blood volume include vasoconstriction. Blood vessels constrict to redirect blood flow to vital organs. Plasma volume recovery. Fluid from the interstitial and intracellular compartments moves into the bloodstream to restore plasma volume. Bone marrow activation. The production of red blood cells increases in the bone marrow to replace lost erythrocytes. Fluid replacement. Drinking fluids or intravenous infusion of fluids helps replenish blood volume. Previous year CSIR net questions. 1. Which of the following hormones increases the reabsorption of water by the kidneys and thus increases blood volume? A. Aldosterone. B. Antidiuretic hormone, ADH. C. Atrial natriuretic peptide, ANP. D. Cortisol. Answer. B. Antidiuretic hormone, ADH. CSIR net life sciences, December 2019. 2. The release of renin is triggered by which of the following conditions? A. Increased blood pressure. B. Decreased blood volume. C. Increased blood osmolarity. D. Increased sodium levels in the blood. Answer. B. Decreased blood volume. CSIR net life sciences, June 2020. 3. The hormone responsible for promoting the excretion of sodium and water to reduce blood volume is aldosterone. B. Angiotensin-2 C-atrial natriuretic peptide, ANP, antidiuretic hormone, ADH. Answer. C-atrial natriuretic peptide, ANP, CSIR, Net Life Sciences, June 2021. Conclusion. Blood volume regulation is essential for maintaining homeostasis in the body. This complex process involves the interaction of the kidneys, hormones such as ADH, aldosterone, and ANP, the sympathetic nervous system, and the lymphatic system. Through these mechanisms, the body can adjust blood volume in response to various stimuli, such as changes in pressure, hydration status, and blood loss, ensuring proper organ function and overall health. You said, blood groups. ChatGPT said, blood groups. Blood groups are classifications of blood based on the presence or absence of specific antigens, proteins, or carbohydrates on the surface of red blood cells, RBCs. These antigens play a crucial role in determining compatibility for blood transfusions, organ transplants, and maternal-fetal interactions. The two significant blood group systems are the ABO blood group system and each blood group system. ABO blood group system. The ABO blood group system was discovered by Carl Landsteiner in 1900. It is based on the presence or absence of two major antigens, A antigen and B antigen. Depending on the combination of these antigens, four primary blood groups are classified. Group A. Antigen. Antigen on the surface of RBCs. Antibodies. Anti-B antibodies present in the plasma. Compatibility. Can receive blood from groups A and O. Can donate to groups A and AB. Group B. Antigen. B antigen on the surface of RBCs. Antibodies. Anti-antibodies present in the plasma. Compatibility. Can receive blood from groups B and O. Can donate to groups B and AB. Group AB. Antigen. Both A and B antigens on the surface of RBCs. Antibodies. No anti-A or anti-B antibodies in the plasma. Compatibility. Universal recipient. Can receive blood from any group A, B, AB, O. Can donate only to group AB. Group O. Antigen. Neither A nor B antigens on the surface of RBCs. Antibodies. Anti-A and anti-B antibodies present in the plasma. Compatibility. Universal donor. Can donate to any group A, B, AB, O. Can only receive blood from group O. Rh blood group system. The Rh blood group system is based on the presence or absence of the Rh factor, also known as the D antigen, on the surface of RBCs. The Rh system is independent of the ABO system, but it plays an essential role in determining blood compatibility. Rh positive, Rh plus if the D antigen is present on the RBC surface. Rh negative, Rh minus if the D antigen is absent from the RBC surface. A person who is Rh positive can receive both Rh positive and Rh negative blood, whereas someone who is Rh negative should only receive Rh negative blood to avoid an immune response. Blood group compatibility in transfusions. Blood transfusions must be carefully matched between the donor and the recipient to avoid a hemolytic reaction, where the immune system attacks the transfused RBCs. Here's how blood group compatibility works for transfusions. Group A can receive from A, O, can donate to A, AB. Group B can receive from B, O, can donate to B, AB. Group AB, universal recipient can receive from A, B, AB, O, can donate to AB. Group O, universal donor can donate to A, B, AB, O, can only receive from O. Rh compatibility in transfusions. Rh positive, Rh plus individuals can receive blood from both Rh positive and Rh negative donors, but Rh negative, Rh minus individuals should only receive blood from Rh negative donors. Blood groups in pregnancy. Blood group incompatibility can also occur during pregnancy, particularly when there is an Rh incompatibility between the mother and the fetus. Rh incompatibility. If an Rh negative mother is carrying an Rh positive fetus inherited from the father, her immune system may recognize the fetal Rh positive RBCs as foreign and mount an immune response. The mother's immune system may produce anti-Rh antibodies, which could cross the placenta and destroy the fetal RBCs, leading to a condition called hemolytic disease of the newborn HDN. To prevent HDN, Rh immunoglobulin injections are given to Rh negative mothers during pregnancy and after childbirth to prevent sensitization. ABO incompatibility. This occurs when the mother's antibodies against her B antigens in her plasma cross the placenta and cause the destruction of fetal RBCs. However, this is usually less severe than Rh incompatibility and often resolves without significant complications. Previous year CSIR net questions. 1. The blood group of an individual is determined by the presence of antigens on the surface of the RBCs, the antibodies in the plasma, C, the composition of plasma protein, C, the hemoglobin content in the blood. Answer. Antigens on the surface of the RBCs, CSIR Net Life Sciences, December 2020. 2. Which of the following blood groups can be a universal donor in a transfusion? A group A. B group B, C group A, B, D group O. Answer. D group O, CSIR Net Life Sciences, June 2019. In an Rh negative mother carrying an Rh positive fetus, what condition may occur if there is Rh incompatibility? A sickle cell anemia. B hemolytic disease of the newborn HDN, C thalassemia. D leukemia. Answer. B hemolytic disease of the newborn HDN, CSIR Net Life Sciences, June 2021. Conclusion. Blood groups are essential for understanding various physiological and medical conditions, especially in transfusion medicine, organ transplantation, and pregnancy. The ABO and Rh systems are the most important in determining compatibility between individuals for blood transfusions and other medical procedures. Blood group incompatibility, particularly Rh incompatibility, can lead to serious health complications, but preventive measures such as the use of Rh immunoglobulin have significantly reduced these risks. Understanding blood groups is critical for safe medical practices and ensuring well individuals in various clinical situations. You said, hemoglobin. ChatGPT said, hemoglobin. Hemoglobin HB is a specialized protein found in red blood cells, RBCs, that is primarily responsible for transporting oxygen from the lungs to tissues and organs and carrying carbon dioxide, CO, back from the tissues to the lungs for exhalation. Hemoglobin is composed of protein subunits called globins and is essential for the efficient functioning of the circulatory system. It is one of the most studied proteins in biochemistry and physiology due to its critical role in maintaining life. Structure of hemoglobin. Hemoglobin is a tetrameric protein, meaning it is made up of 4 subunits. These subunits consist of 2 alpha-alpha chains and 2 beta-beta chains, each associated with a heme group. The heme group contains an iron atom, face squared, that binds oxygen. Each hemoglobin molecule can bind 4 molecules of oxygen, one per heme group, forming a fully saturated structure. Globin chains. The alpha globin and beta globin chains are folded into specific structures, and they are produced from distinct genes. Hemoglobin structure is crucial for its ability to change its shape and release or bind oxygen depending on environmental conditions, e.g., oxygen concentration and pH. Heme group. Each heme group contains an iron atom that binds oxygen. The iron atom can form a reversible bond with one oxygen molecule, which is critical for hemoglobin's oxygen carrying capacity. Quaternary structure. Hemoglobin's quaternary structure is dynamic, allowing it to undergo conformational changes when oxygen binds or is released. This is known as the cooperative binding effect. Function of hemoglobin. Oxygen transport. The primary function of hemoglobin is to bind oxygen in the lungs and transport it through the bloodstream to tissues that require oxygen. The affinity of hemoglobin for oxygen changes based on the partial pressure of oxygen co. In the lungs, where the oxygen concentration is high, hemoglobin binds oxygen. In tissues with low oxygen concentrations, such as muscle tissues during exercise, hemoglobin releases oxygen. CO transport. Hemoglobin also helps in transporting carbon dioxide, a metabolic waste product, from the tissues to the lungs. About 20% of CO is carried by hemoglobin, while the rest is dissolved in the plasma or converted into bicarbonate ions HCO. Buffering. Hemoglobin acts as a buffer in the blood, helping to maintain the pH of the blood by binding to free hydrogen ions H when the pH drops, as in the tissues during co-release, and releasing them when the pH increases. Oxygen dissociation curve. The oxygen dissociation curve, also called the oxygen hemoglobin dissociation curve, is a graphical representation of the relationship between the partial pressure of oxygen and the oxygen of hemoglobin. The curve exhibits sigmoidal S-shaped characteristics, which reflects cooperative binding. The binding of oxygen to one subunit of hemoglobin increases the affinity of the other subunits for oxygen, facilitating oxygen uptake and release. Key factors that influence this curve include partial pressure of oxygen. As the increases in the lungs, hemoglobin binds more oxygen. Conversely, as decreases in tissues, hemoglobin releases oxygen. PCO partial pressure of carbon dioxide. Higher PCO levels, as in